There is a galaxy you can see tonight with your own eyes. No telescope needed, no special equipment, no particular knowledge of where to look beyond the name of a constellation. On a clear autumn evening in the northern hemisphere, if you find a moment of real darkness away from city lights, you can look toward the constellation Andromeda and find a faint, gentle smudge of light hanging there among the stars, soft and slightly blurred, easy to overlook, easy to mistake for a wisp of something ordinary. Ancient astronomers, who spent their lives cataloging and naming what they saw in the night sky, assumed it was a cloud of gas within our own stellar neighborhood. For centuries, that is what everyone believed. The idea that it might be something far larger, something as vast and complete as an entire galaxy of stars, didn't seriously enter scientific thinking until the early 20th century. When the truth finally came into focus, it expanded the known size of the universe in a single stroke. It transformed that quiet smudge from a local curiosity into a structure containing roughly 1 trillion stars, burning and turning across a disk of space more than 220,000 light-years wide, located 2.5 million light-years from the planet you are resting on tonight. That distance, 2.5 million light-years, is the distance this story is really about. Not the galaxy itself, and not the Earth, and not the vast emptiness of our own solar system, though we will visit all of those things along the way. The story is about scale, about the way the universe is organized at sizes so much larger than anything human intuition was built to process, that the numbers begin to lose their grip on meaning and become something closer to poetry. The numbers are real. They are measured, confirmed, published, and verified. But they describe a reality so far removed from the one. Your nervous system evolved to navigate that your mind has almost no purchase on them. What we can do, slowly and carefully, is try to approach them, to build up to them one step at a time, so that by the time we arrive at that 2.5 million light-year gap, we have some sense of the journey it took to get there. So let us begin somewhere familiar. Let us begin with the ground beneath you. The Earth, measured across its equatorial circumference, spans approximately 24,900 miles. That is the distance you would need to travel if you wanted to circle the planet and return to where you started. At the speed of a commercial airliner cruising at around 550 miles per hour, that uninterrupted journey takes just over 45 hours, nearly 2 full days of continuous flight to trace the outline of the world you live on. At the speed of a car traveling steadily at 70 miles per hour, the same trip takes roughly 14.5 days, 2 full weeks of driving without rest, around the circumference of a single planet, that is Earth at human speed. And it genuinely is enormous by the standards your body evolved to apply. For most of human history, people spent their entire lives within a few hundred miles of where they were born. The planet's full circumference was something no individual could meaningfully experience. Even today, even with jet travel and GPS navigation and real-time satellite imagery of every corner of the surface, the sheer physical size of the world retains a kind of overwhelming quality. Oceans take hours to cross by air. Continents take days to drive across. The planet is built at a scale that exceeds what human biology was designed to process. And yet, this sense of the Earth's enormity, which is real, which is not an illusion, turns out to be the very first thing we need to gently set aside. If you go vertical, the same recalibration begins almost immediately. The deepest point in Earth's oceans is located in a region of the Western Pacific called the Challenger Deep. At the southern end of the Mariana Trench, the depth there reaches approximately 36,000 feet below the surface, which works out to nearly 7 miles straight down. Reaching that depth requires a specially designed submersible built to withstand pressures exceeding 16,000 pounds per square inch, roughly 1,000 times the atmospheric pressure you feel standing at sea level. The water there is just a few degrees above freezing. Sunlight disappears within the first few hundred feet. Below that, the ocean exists in total, permanent darkness. Fewer than 30 people in all of recorded human history have ever descended to the bottom of the Challenger Deep. Each of those descents required engineering of extraordinary precision and decades of development. By every human measure, the Challenger Deep is profound. It is remote, hostile, almost impossible to reach, alien in every sensory respect to the world above. But Earth's diameter is approximately 7,918 miles. The Mariana Trench, the deepest scar on our planet's surface, is a feature less than 7 miles deep on a sphere nearly 8,000 miles across. If you shrank the Earth down to the size of a standard basketball, the Challenger Deep would be imperceptible to your fingertip. You could run your hand across the entire surface of that basketball, and the single deepest point in all the world's oceans would register as nothing. No texture, no indentation, just smooth, uninterrupted surface. The feature that challenged human engineering and limited human exploration to fewer than 30 individuals across all of history is, at planetary scale, a rounding error. This is the first lesson in what happens when you change the scale of your perspective. Things that feel enormous at one level of magnification become invisible at the next. The pattern repeats at every scale we are going to visit, and each time it repeats, the thing that seemed immense will be the thing that disappears. We have not yet left the planet. Earth travels around the Sun at an average distance of approximately 93 million miles. Astronomers call this distance one astronomical unit, and it serves as the baseline measurement for everything else in the solar system. 93 million miles, at the speed of that same commercial airliner. Traveling continuously without landing or refueling, the journey to the Sun would take more than 19 years. A child born the day you departed would be approaching adulthood by the time you arrived. At the speed of a bullet from a high-powered rifle, roughly 1,700 miles per hour, the same journey takes more than 6 years. And light, the fastest phenomenon in the known universe, traveling at approximately 186,000 miles per second, requires 8 minutes and 20 seconds to cross that distance. 8 minutes and 20 seconds from the surface of the Sun to your eyes. This means that when you look at the Sun, you are not seeing it as it exists at this moment. You are seeing it as it was a little over 8 minutes ago. If the Sun were to vanish entirely, if it simply ceased to exist at this instant, you would not know for 8 minutes and 20 seconds. You would still feel warmth. You would still see light in the sky. The world would appear to continue as normal for the time it takes to brew a pot of coffee, because the information of what happened would still be traveling toward you at the fastest speed the universe allows. That is the distance between us and our own star. The Sun itself is a structure that makes Earth look small in ways that are difficult to absorb all at once. Its diameter reaches approximately 864,000 miles, about 109 times the diameter of Earth. 109. Earths placed side by side would just barely span the Sun's face from edge to edge. In terms of volume, the comparison grows even more striking. Roughly 1 3/10 million Earths could fit inside the Sun's volume. 1.3 million. Not beside it, inside it. Every mountain range and ocean and desert and city on Earth, replicated 1.3 million times over, and the Sun would contain all of it with room. Remaining, what you see rising in the east each morning is a sphere of superheated plasma so massive that it holds 99.86% of all the matter in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, Every grain of dust drifting between planetary orbits comprises the remaining 0.14%. Jupiter, the largest planet, which could contain more than 1,300 Earths within its own volume, is a gravitational footnote in comparison to the Sun. Earth doesn't even reach footnote status. The Sun converts approximately 4 million tons of its own mass into pure energy every second through nuclear fusion. 4 million tons per second, not per year or per day, but per tick of the clock. It has been sustaining this output continuously for approximately 4.5 billion years and will continue for roughly another 5 billion before it exhausts its hydrogen fuel and begins the long transformation into a red giant. In the broad sweep of stellar types, our Sun is unremarkable, a middle-aged, middleweight, average luminosity star of the most common variety, classified as a G-type, main sequence star. There is nothing especially unusual about it. By some measures, that is one of the stranger realizations astronomy offers. The object that makes all life on Earth possible, the star around which our entire existence is organized, is profoundly average among the hundreds of billions of stars in our galaxy. Moving outward from the Sun, the planets arrange themselves at distances that begin to stretch the imagination in a different direction. Mars orbits at approximately 142 million miles. Jupiter, the first of the gas giants, circles at roughly 484 million miles. Saturn drifts at about 886 million miles. Uranus at approximately 1.8 billion miles. And Neptune, the outermost recognized major planet, completes its orbit at a distance of about 2.8 billion miles from the Sun. A beam of light leaving the Sun takes more than 4 hours to reach Neptune if a spacecraft near Neptune sent a radio signal back to Earth, a signal traveling at the absolute speed limit of the universe. It would take approximately 4 hours to arrive. Any response would take another 4 hours to travel back. 8 hours of round-trip communication delay at the fastest speed physics permits. For all practical purposes, a spacecraft operating near Neptune is alone. There is no real-time guidance, no possibility of corrective instruction in the moment. This is not theoretical. It has been the lived reality of every deep space mission our civilization has ever flown. When NASA's New Horizons spacecraft made its closest approach to Pluto in the summer of 2015, the encounter unfolded entirely on autopilot. Mission controllers had uploaded the flyby instructions hours in advance. Because the one-way signal travel time to Pluto exceeded 4.5 hours, there was no possibility of course correction during the encounter. The spacecraft executed its observations alone, stored the data on board, and then spent more than 15 months transmitting the results back to Earth at a data rate of roughly 1 to 2 kilobits per second, slow enough that downloading the full dataset from a flyby lasting hours required more than a year, and Pluto is nowhere near the outer boundary of the Sun's domain. Voyager 1, launched in September of 1977, and now more than 15 billion miles from Earth after nearly 5 decades of continuous travel, communicates home via a radio transmitter running at roughly 22 watts, about the power of a dim light bulb. By the time that signal crosses 15 billion miles and reaches the antennas of NASA's Deep Space Network on Earth, the received power measures approximately 1/10 trillionth of a watt. That is roughly 10 billion times weaker than the power needed to run a standard digital wristwatch. Engineers use cryogenically cooled receivers and hours of signal averaging just to extract useful information from the background noise, and Voyager 1 has not yet left the Sun's gravitational sphere of influence. It is still, by any meaningful definition, within our solar system, The Sun's gravitational reach extends far beyond the last major planet. Beyond Neptune lies the Kuiper Belt, a ring of icy bodies stretching from roughly 30 to 50 astronomical units from the Sun. Beyond that lies the scattered disk, and farther still the hypothesized Oort cloud, a vast spherical shell of icy objects thought to extend from perhaps 2002 as far as 100,000 astronomical units from the Sun. 1 light year equals approximately 5.88 trillion miles. The full gravitational domain of our single, unremarkable, middle-aged star spans a sphere potentially 2 to 3 light-years in diameter. At its current speed, Voyager 1 would need approximately 73,000 years to cover the distance to Proxima Centauri, the nearest star to our Sun. 73,000 years. That is roughly 9 times longer than all of recorded human civilization to make the emptiness of the solar system feel physical. Consider a scale model. Shrink the Sun to the size of a large grapefruit, roughly 8 inches across. At that scale, Earth becomes a small pebble less than an inch across, sitting about 75 feet away. Mars is a slightly smaller pebble at around 115 feet. Jupiter, the largest planet in our system, becomes a ball about 6 inches in diameter, floating at roughly 390 feet from the Sun. Saturn appears at about 717 feet. Neptune, the outermost major planet, is a ball slightly smaller than Jupiter, sitting nearly half a mile away. Half a mile. And the Sun in this model is an object you could hold in one hand. The solar system at this scale spans a small town, and nearly every square foot of that town is completely empty. No buildings, no objects. Nothing between a grapefruit near one end and a scattering of small balls stretching toward the horizon. The model is mostly emptiness. The planets are the exception. The emptiness is the rule. But the step in this model that most clearly reveals the nature of interstellar space is what happens when you look for the nearest neighboring star. At the same scale, with the Sun as a grapefruit and Earth as a small pebble 75 feet away, Proxima Centauri, the closest star to our Sun, would be located approximately 4,000 miles away. If you placed the Sun grapefruit in the center of New York City, the nearest neighboring star would be another object the same size, sitting somewhere in the middle of the Pacific Ocean, halfway to Japan. 4,000 miles of empty, featureless terrain between one star and its nearest neighbor. The gap between stars is not simply larger than the gap between planets. It belongs to a qualitatively different category of distance. The space between stars is also not entirely passive. The interstellar medium, the thin material filling the spaces between stars in our region of the galaxy, contains on average roughly 1 atom per cubic centimeter. That sounds like almost nothing, and compared to any environment on Earth, it is nearly nothing. The air in a typical room contains approximately 25 billion molecules per cubic centimeter, but the interstellar medium is not perfectly empty. It carries stray hydrogen and helium atoms, trace amounts of heavier elements, microscopic dust grains, and a constant bath of high-energy cosmic ray particles. Charged particles accelerated to near light speed by distant supernova and other energetic astrophysical events. Magnetic fields thread through it, weak but real, stretching across light-years of space. For a spacecraft traveling at the modest speeds of Voyager 1, this material is irrelevant, too sparse to produce measurable drag or damage. But for a spacecraft traveling at any significant fraction of light speed, the interstellar medium transforms from an invisible background into a serious physical problem. At 10% of light speed, approximately 67 million miles per hour, individual hydrogen atoms encountered by the spacecraft would strike the hull with the energy of a high-energy particle accelerator collision. The cumulative bombardment from trillions upon trillions of such impacts over the course of a 4-light-year journey to Proxima Centauri would deliver a punishing dose of radiation, erode shielding materials, and potentially degrade instruments beyond function. Microscopic dust grains, traveling at that relative velocity, would carry the kinetic energy of small explosive charges on impact. The void between stars is not a passive emptiness. It is a thin, invisible environment that grows more hazardous the faster you attempt to cross it. And this is all still within our own solar neighborhood. Everything described so far, the planets, the empty spaces between them, Voyager 1 and its 15 billion miles of travel exists inside a single galaxy. The Milky Way, a structure so large that if you placed a grain of rice at the 50-yard line of an American football field and called that grain the entire solar system, the Milky Way would extend far beyond the stadium, beyond the parking lot, beyond the surrounding city, out to distances the football field cannot even begin to suggest. The grain of rice sitting at midfield would be invisible to anyone in the stands. You could walk down to the field, drop to your knees, and search the turf with a magnifying glass, and still struggle to find it. The Milky Way is a barred spiral galaxy. Seen from far above, it would look like a vast pinwheel, curved arms of stars, gas, and dust spiraling outward from a dense central bar of older, reddish stars, everything slowly turning together around a common center. The disk of visible stars measures approximately 100,000 light-years in diameter. To cross it, traveling at the speed of light, the absolute fastest anything can move in this universe, would take 100,000 years. A beam of light that departed from one edge of the Milky Way on the day you were born would not reach the opposite edge until roughly 100,000 years after every trace of human civilization had crumbled and been forgotten. That is the width of our home galaxy. The disk itself is relatively thin in comparison to its width, about 2,000 light-years thick in the region near our Sun. But even that thinness represents an enormous vertical distance. Light needs 2,000 years to travel from the upper surface of the galactic disk to the lower surface in our neighborhood. When the Romans were constructing their first roads across Europe, a photon leaving the top of the Milky Way's disk near our position had only then begun a journey that would end at the bottom of the disk around now. 2,000 years of travel at the fastest speed the universe allows, just across the thin edge of the galaxy we inhabit. Within this disk, the Milky Way contains somewhere between 200 billion and 400 billion individual stars. The exact count remains uncertain because our position inside the galaxy limits our ability to observe stars on the far side, where thick clouds of interstellar dust block visible light. Infrared surveys have improved our estimates considerably, but a precise census of every star in the Milky Way remains beyond current capability. What we know with confidence is that the number is staggering. If you attempted to count every star in the galaxy at a rate of 1 per second, without ever pausing, the task would take somewhere between 6,300 and 12,700 years. You would need to begin counting before the construction of the Egyptian pyramids and continue without interruption far past the present day. Each of those hundreds of billions of stars is a sun. Some are enormous, blue supergiants, burning with luminosities exceeding 100,000 times the output of our own sun, blazing hot and short-lived in cosmic terms. Others are red hypergiants, so vast in diameter that if one were placed at the center of our solar system, its surface would extend past the orbit of Jupiter. Still others are red dwarfs, small and dim enough that not a single one is visible to the naked eye from Earth, despite the fact that they are by far the most common type of star in the galaxy. Roughly 70% of all stars fall into this category. Our sun is somewhere in the middle of the stellar spectrum, brighter than most, dimmer than many, larger than some, smaller than others. In a galaxy of hundreds of billions, our star is deeply, unremarkably average. Our solar system sits approximately 26,000 light-years from the galactic center. We are not near the core, that dense, active region where stars are packed thousands of times more tightly than in our neighborhood. We're a supermassive black hole called Sagittarius A star, anchors the entire structure with a mass of roughly 4 million times the mass of our sun. But we are not at the edge of the galaxy either. We occupy a position roughly halfway out along the disk, embedded in a minor structure called the Orion Spur, which branches off between two of the galaxy's major spiral arms. In galactic terms, we live in the suburbs, not the busy downtown, not the thinning outskirts, but somewhere quiet and average in between. The sun and everything gravitationally bound to it orbits the galactic center at approximately 515,000 miles per hour. Despite this extraordinary speed, faster than any human-made object has ever traveled, the sheer scale of the Milky Way means that one complete orbit takes roughly 230 million years. Astronomers call this period a galactic year. Our solar system is approximately 20 galactic years old. The last time Earth was in its current position in the galaxy, dinosaurs had not yet appeared. During that single orbit, the continents have drifted. The climate has changed multiple times. Entire classes of organisms have evolved and gone extinct. If you were standing at the center of the Milky Way and tried to locate our sun among the hundreds of billions of stars spread across the disk, the task would be essentially impossible. It would be something like standing in the middle of a completely darkened Manhattan at night, trying to identify one specific firefly hovering somewhere among 400 billion others scattered across the island. Every firefly glowing, every firefly moving. The one you are looking for, utterly average in brightness and size, located in a section of the island with no distinguishing features. You would never find it. Not in a human lifetime, not in 1,000. Every constellation you have ever seen in the night sky is a local structure, a small cluster of nearby stars that happen to fall in interesting patterns. When viewed from this particular vantage point in the disk, every meteor shower, every aurora, every planet visible to the naked eye, all of it occurs within this single galaxy. When you look up on a dark, clear night and see that soft pale band of light stretching across the sky, the river of light that gave the galaxy its name, you are seeing the combined glow of billions of distant stars in the galactic disk, individually too far away to resolve, blending together into a luminous smear. That river is your home, and it is not the largest thing in our immediate cosmic neighborhood. The story of how we came to know that begins on a night in the early 1920s, at an observatory perched above the Los Angeles basin in the mountains near Pasadena. The scientific community at the time was engaged in what came to be called the Great Debate, a genuine, unresolved disagreement among professional astronomers about the nature of the fuzzy spiral objects visible in telescopes throughout the sky. One side held that these objects were relatively nearby clouds of gas within the Milky Way local features, in what they assumed was the totality of the universe. The other side suspected they were something far more dramatic, entire island universes, complete galaxies in their own right, located at distances so vast they lay beyond the Milky Way's borders entirely. Neither side had definitive evidence. The debate remained unresolved and increasingly contentious. As observational technology gradually improved, what settled it was a pulsating star, Edwin Hubble, working with the Hooker telescope at Mount Wilson Observatory, the largest operational telescope on Earth at that time, spent months during 1923 and 1924 making long photographic exposures, aimed at the Andromeda Nebula, as it was then called. The Hooker telescope gathered enough light to do something no earlier instrument could: resolve individual stars within the nebula, separating what had appeared as a diffuse glow into discrete points of light. Among those resolved stars, Hubble identified a Kithide variable, a type of star whose brightness rises and falls in a predictable, regular cycle. The significance of this identification came from the earlier work of astronomer Henrietta Swan Leavitt, who had made a discovery of extraordinary scientific consequence through years of careful, painstaking observation, working with photographic plates of Kithide variables in the Magellanic Clouds, companion structures to the Milky Way visible from the southern hemisphere. Leavitt noticed that the pulsation period of a Kithide star was directly related to its intrinsic luminosity. A Kithide that completed its cycle slowly was genuinely, intrinsically brighter than one that cycled rapidly. This period luminosity relationship transformed Kithide variables into cosmic measuring tools of remarkable precision. By observing how fast a Kithide pulsated, you could determine how truly bright it was. By comparing that true brightness to how bright it appeared from Earth, you could calculate the distance using the straightforward physics of how light dims with distance. Hubble applied this method to the Kithide he had found in the Andromeda Nebula. The pulsation period told him the star's true luminosity. Its faintness as seen from Earth told him it was enormously far away. When he completed the calculation, the result exceeded the estimated diameter of the Milky Way by a wide margin. Later refined with better distance measurement techniques over subsequent decades, the distance to Andromeda settled at approximately 2.5 million light-years, a number that placed it definitively outside our galaxy. The Andromeda Nebula was not a gas cloud. It was a separate galaxy, an island of stars at a distance that made the Milky Way itself look like a small island in a vast sea dot in a single observation, with a single Kithide variable on a photographic plate. The known size of the universe expanded from one galaxy to at least two. Everything human beings had ever thought about the cosmos, every model of scale and structure and position, was revised overnight. The great debate was over. That faint smudge you can see in the autumn sky is the Andromeda Galaxy, catalogued as Messier 31. It is the most distant object visible to the unaided human eye, and what you are looking at, that barely perceptible haze, is the combined light of approximately 1 trillion stars. Not 1 billion, 1 trillion. The Milky Way, depending on which estimate you accept, contains between 200 billion and 400 billion stars. Andromeda contains roughly 1 trillion, between 2.5 and 5 times as many as our home galaxy, depending on the comparison you use. Every star in the Milky Way could be multiplied several times over, and the result might still not match the stellar population of the galaxy next door. Andromeda's disk stretches across approximately 220,000 light-years. The Milky Way's disk spans about 100,000. Placed side by side, Andromeda would dwarf our galaxy the way a beach ball dwarfs a tennis ball. More than double the diameter means far more than double the area. The surface area of Andromeda's disk is roughly 4 to 5 times that of the Milky Way. It is not simply a scaled-up version of our galaxy. It is a categorically larger structure, a galactic giant that makes our home look like the smaller companion. The structural differences extend deeper than raw size. Andromeda is also a spiral galaxy, but its spiral arms are more tightly wound, and its central bulge, the dense concentration of older stars surrounding the galactic core, is significantly more prominent than the Milky Way's. The size and shape of a galaxy's central bulge reflects its history of mergers with other galaxies. Larger bulges typically indicate more past collisions. Andromeda's prominent central concentration suggests it has consumed more satellite galaxies across its long history than the Milky Way has, growing its central regions through repeated gravitational events. Spanning billions of years, both galaxies harbor supermassive black holes at their centers. In the Milky Way, the central black hole is designated Sagittarius A star, and it carries a mass approximately 4 million times the mass of our Sun. That is enormous by any scale a human being can relate to. But Andromeda's central black hole, sometimes called M31 star, has a mass of approximately 100 million solar masses. That is roughly 25 times heavier than our galaxy's central black hole. The difference in central black hole mass between the two galaxies reflects the difference in their accretion histories. Larger black holes grow by consuming more material over cosmic time, fed by infalling gas and by mergers with smaller black holes, brought in by absorbed satellite galaxies. The globular cluster populations of each galaxy add another layer of comparison. Globular clusters are ancient, dense, spherical collections of stars, some of the oldest structures in any galaxy, with many dating back to within 1 billion years of the Big Bang. The Milky Way possesses approximately 150 known globular clusters. Andromeda has roughly 450, and some estimates push that number higher, toward 500 or more. Each globular cluster contains anywhere from tens of thousands to several million stars, packed into a spherical volume only a few dozen to a few hundred light-years across. Andromeda's richer globular cluster system speaks to its larger gravitational sphere of influence and its more extensive history of absorbing smaller companion galaxies. Across cosmic time, Andromeda also commands a substantial gravitational entourage of smaller satellite galaxies. Its two most prominent companions are designated M32 and M110, both visible in long-exposure photographs of Andromeda as distinct, smaller structures near the main disk. M32 is a compact elliptical galaxy containing roughly 3 billion stars. It orbits remarkably close to Andromeda's disk and shows clear evidence of tidal stripping. Andromeda's gravity is actively pulling stars away from M32's outer regions, slowly dismantling it. Simulations suggest that M32 may once have been a much larger galaxy, progressively consumed by billions of years of close gravitational interaction. Beyond these companions, Andromeda possesses at least 35 confirmed satellite galaxies and likely harbors more awaiting discovery in future deep surveys. The question of which galaxy is more massive overall is more complicated than the visual comparison might suggest. Galaxy mass includes not just visible stars and gas, but the vast invisible halos of dark matter that surround every large galaxy, halos that extend far beyond the visible disk, sometimes reaching several 100,000 light-years from the galactic center. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes in any wavelength. Its presence is inferred entirely through its gravitational effects, the rotation speeds of stars within a galaxy, the orbital behavior of satellite galaxies, the way background light bends as it passes through a galaxy's gravitational field. Earlier estimates placed Andromeda's total mass, including its dark matter halo, at roughly 1.5 to 2 trillion solar masses, comfortably larger than the Milky Way's estimated total of 1 to 1.5 trillion solar masses. But more recent analyses, particularly those using data from the European Space Agency's Gaia spacecraft, have produced revised and lower estimates for Andromeda's mass, with some studies arriving at figures closer to 800 billion solar masses, potentially comparable to, or even slightly less than the Milky Way's own total. Other studies using different methodologies produce higher estimates. What this means in practical terms is that while Andromeda is unambiguously larger in disk diameter, star count, central black hole mass, and globular cluster population, the question of which galaxy is more massive overall remains an active area of scientific investigation. The two galaxies may be closer to equal in total mass than decades of popular astronomy assumed. Both galaxies belong to a larger gravitational grouping, called the local group, a collection of more than 80 individual galaxies, most of them small dwarf galaxies containing only a few billion stars or fewer, loosely held together by mutual gravitational attraction across a region roughly 10 million light-years wide. The third largest member is the Triangulum galaxy, sometimes called M33, which contains approximately 40 billion stars and sits roughly 3 million light-years from us. The Milky Way and Andromeda are the two dominant members of this group, each at the center of its own smaller cluster of satellite and companion galaxies, and together accounting for the overwhelming majority of the group's total stellar population. The Milky Way has approximately 50 known satellite galaxies, including the large and small Magellanic Clouds, visible from the southern hemisphere as detached patches of light. Andromeda has a comparable or slightly larger collection of dwarf companions. These smaller galaxies are slowly being drawn inward by their host galaxy's gravity, and many will eventually be torn apart and absorbed, their stars scattered into the vast stellar halos surrounding whichever giant claimed them. Both the Milky Way and Andromeda are not sitting still. They are not maintaining a polite distance in a quiet region of space. They are moving toward each other. This has been known since 1912, when astronomer Vestos, working at Lowell Observatory in Flagstaff, Arizona, measured the spectrum of Andromeda's light and found it shifted toward the blue end of the spectrum. When an object moves toward an observer, the wavelengths of light it emits are compressed, shifted toward shorter, bluer wavelengths. This blue shift is the light equivalent of the rising pitch of a siren approaching you. Andromeda's light is blue. The galaxy is getting closer. The measurement has been confirmed and refined continuously in the centuries since Slipher's initial observation. The current best estimate for Andromeda's approach speed, measured along the direct line between the two galaxies, is approximately 110 kilometers per second, which translates to roughly 250,000 miles per hour. Every second, the gap between our galaxy and Andromeda shrinks by 110 kilometers. Every year, approximately 3.5 billion kilometers are erased from the intergalactic distance. That sounds like rapid progress. By any terrestrial standard, it is. 250,000 miles per hour exceeds the speed of any human-made object ever built. It is fast enough to travel from Earth to the Moon in about an hour, but against the full scale of intergalactic space, 250,000 miles per hour is glacially slow. At that rate, closing the complete 2.5 million light-year gap between the Milky Way and Andromeda would take roughly 4 to 5 billion years, approximately the same amount of time the Earth has already existed. The approach has been underway for billions of years already. It will continue for billions more. You will not notice it. No civilization during any reasonable span of human existence will notice any visible change in Andromeda position through naked eye observation. This is also where the science becomes somewhat more complex than the widely repeated popular account suggests. For decades, the standard description of the Milky Way-Andromeda situation was fairly simple. The two galaxies are on a collision course. They will impact head-on in approximately 4 to 4.5 billion years, and the result will be a single merged elliptical galaxy. This version of the story has appeared in countless documentaries, textbooks, and planetarium presentations. It is one of the most widely known facts in popular astronomy. The actual scientific picture is more nuanced, and our understanding has evolved in meaningful ways over the past decade. The radial velocity, the speed at which Andromeda approaches us directly, is well measured and not in serious dispute. But radial velocity only tells you how fast the gap is closing along the straight line between the two galaxies. It says nothing about whether Andromeda is moving sideways relative to that line. This sideways component, called the transverse velocity, is critically important for predicting the geometry of the encounter. A large transverse velocity could mean the two galaxies pass each other on the first approach rather than colliding head-on, before gravity eventually pulls them back together for a later, closer encounter. Measuring the transverse velocity of a galaxy 2.5 million light-years away is extremely difficult. The sideways motion translates into an angular shift on the sky so small as to be nearly undetectable with older instruments. For years, it was essentially unconstrained, and models typically assumed it was small enough that a direct collision remained the most probable outcome. The Gaia spacecraft, designed to measure the precise positions and motions of stars with unprecedented accuracy, changed that situation. By tracking the average motion of stars within Andromeda relative to extremely distant background quasars, researchers were able to derive the first robust constraints on Andromeda's sideways motion. Studies published in 2019, using the second data release from Gaia, estimated Andromeda's transverse velocity at approximately 57 kilometers per second, with uncertainties spanning roughly 40 to 70 kilometers per second. This is not a negligible value. A significant transverse component means the two galaxies are not approaching each other in a straight line. They are on a path that includes a meaningful sideways offset. What does this mean for the interaction? Primarily, it makes a direct head-on collision on the first pass somewhat less likely and a glancing encounter more probable. Instead of a single dramatic impact, the galaxies might execute an initial flyby, passing close enough for their outer stellar populations and dark matter halos to interact gravitationally, but without the immediate, complete merger that earlier models predicted. After this first pass, gravitational friction, the gradual dissipation of orbital energy as the two galaxies move through each other's material, would slow their relative motion. Gravity would pull them back toward each other for a second approach, closer and slower than the first. Subsequent passes would follow, each one bringing the two systems more thoroughly together, until eventually, over a period, potentially spanning several billion years after the first close encounter, they coalesce into a single, larger structure. This revised scenario pushes the timeline for a full merger considerably further into the future than the widely cited, for 4.5 billion years, perhaps to 5 or 6 billion years for a first close encounter, with the final coalescence possibly not occurring until 8 to 10 billion years from now. Some models fall at the earlier end of this range, others at the later end. The honest scientific position is that a significant gravitational interaction is certain. The blue shift is real. The gravitational attraction is real. Some form of close encounter will happen. What remains under active investigation is the precise geometry and timeline, whether the first pass is head-on or glancing, how many orbits or passes occur before final coalescence, and what the end product looks like. The popular image of a galactic collision, fireballs, crashing stars, exploding planets, wholesale destruction, is almost entirely wrong. A galaxy merger is not a collision in any sense that connects to human experience. Stars within galaxies are separated by truly enormous distances relative to their physical sizes. In our region of the galaxy, the average gap between neighboring stars is roughly 4 to 5 light-years. Each star spans a few 100,000 to a few million miles in diameter. but the spaces between them cover trillions of miles. If you shrank the sun to the size of a bowling ball and placed it in the center of a large auditorium, the nearest neighboring bowling ball, representing the nearest star, would be located in a different city hundreds of miles away. The two bowling balls could pass quite close to each other by galactic standards and never come anywhere near touching dot when two galaxies pass through or near each other. The probability of any two stars physically colliding is vanishingly small, statistically negligible. The galaxies are structured almost entirely of empty space, two vast collections of emptiness passing through each other. What does happen is gravitationally profound. The tidal forces involved during a galactic encounter operate across scales of thousands of light years and reshape both galaxies dramatically, without ever requiring individual stars to make contact. These forces warp stellar orbits, stretch and distort spiral arms, fling some stars into entirely new trajectories that carry them into intergalactic space, and pull others deep into the merged galactic core. The organized, elegant spiral structures of the Milky Way and Andromeda would be progressively distorted, twisted, and eventually dissolved. The orderly disk shapes would give way to something more chaotic, streams and shells of stars in randomized orbits, gradually settling into a rounder, less structured form. Meanwhile, the gas within both galaxies responds very differently from the stars. Stars, being compact and widely separated, pass through each other's galactic space without directly interacting. But gas clouds are extended and diffuse. When the gas from two merging galaxies meets, it collides, compresses, and heats. This compression triggers enormous waves of new star formation. Entire regions that had been quiet for billions of years would suddenly light up with the birth of millions of new stars, blazing in infrared and ultraviolet radiation. Astronomers observe this phenomenon in real time in other merging galaxy pairs scattered across the observable universe. The antennae galaxies, two spirals currently in the process of merging roughly 63 million light-years from Earth, show spectacular bursts of triggered star formation in their overlapping regions, matching model predictions. The mice galaxies, designated NGC 4676, showed two spirals caught at an earlier stage, their long tidal tails streaming outward like slow-motion wakes, stretching hundreds of thousands of light-years into intergalactic space. The Cartwheel Galaxy, formed when a smaller galaxy punched directly through the center of a larger spiral at high velocity, shows an expanding ring of triggered star formation radiating outward like a ripple on a cosmic pond, with the smaller intruder galaxy still visible nearby. These are not simulations. They are real galaxies, observed at various stages of gravitational interaction, providing a living catalogue of what different phases of a merger look like. Astronomers study them as proxies for our own galaxy's eventual future, using their observed properties to calibrate and validate the computer models of the Milky Way Andromeda encounter. The starburst phase that accompanies the early stages of a merger is temporary. The available gas is eventually either converted into new stars, heated beyond the temperatures at which it can collapse, or expelled from the system by the intense energy output of newly formed stars and any active galactic nuclei triggered by gas falling toward the central black holes. After the starburst quiets, star formation declines sharply. The merged galaxy begins to settle. The end state, reached perhaps 1 to 2 billion years after final coalescence, would be a massive elliptical galaxy. No spiral arms, no disk, just a roughly spherical or slightly elongated cloud of stars orbiting a common center in largely randomized directions, held together by gravity. Some astronomers have suggested calling the result Milky Andromeda, though the name is informal and the structure it refers to would be anything but. a combined system containing somewhere between 1.5 and 2 trillion stars, with a total mass potentially exceeding 2 trillion solar masses, dominated by 1 or 2 supermassive black holes at its core, which would themselves eventually spiral together in a merger, producing gravitational waves that could, in principle, be detected across much of the observable universe. As for our own solar system, if it still exists at the time of the first close encounter, which depends on the precise timeline, given that the Sun will exhaust its hydrogen fuel in approximately 5 billion years, the most likely outcome is not destruction, but displacement. The Sun is unlikely to collide with any other star, for all the same reasons that stellar collisions are statistically negligible across the entire merger. But gravitational perturbations from the encounter could significantly alter the Sun's orbit within the merged galaxy. It might be thrown outward into the halo, orbiting far from the galactic center at greatly increased distance. It might be pulled inward. In some simulation runs, a small fraction of stars are ejected entirely from the merged system, flung out into intergalactic space at high velocity, becoming unbound rogues drifting through the void with no galactic home. From the perspective of any inhabitants on a planet orbiting a star caught in this merger, the changes would be imperceptible on human timescales. Galactic mergers unfold across hundreds of millions of years. The night sky would change only gradually, across millennia and then millions of years. Stars from Andromeda would slowly appear in unfamiliar constellations that gradually distorted into shapes no human had ever seen. The pale band of the Milky Way across the sky would warp, brighten in some regions, dim in others, and eventually dissolve into a more diffuse, uniform glow as the disk structure was gradually destroyed. New nebulae would appear as triggered star formation erupted across regions of compressed gas. But none of this would be perceptible on a human lifetime. A galactic merger is measured in geological time, not human time. It would be like watching a mountain erode, real, powerful, transformative, and utterly imperceptible in the moment. Now we arrive at the distance itself. And this is where the numbers stop behaving like numbers. 2.5 million light. That is the gap between the Milky Way and the Andromeda galaxy. Let us spend a moment honestly trying to understand what it means. A light year is the distance that light travels in 1 year, moving at approximately 186,000 miles per second. In more familiar terms, 1 light year equals roughly 5.88 trillion miles. 5,880 billion miles. Written out in full, that number has 13 digits. A single light year is already so far beyond anything a human being has ever physically traversed that it functions more as a mathematical concept than a practical distance. No human being has traveled even 1% of 1% of 1 light year from Earth. Farthest any person has ever been from this planet is the distance to the Moon, approximately 240,000 miles during the Apollo missions. 1 light year is roughly 24 million times farther than the Moon. Every crewed space mission in human history, every walk on the lunar surface, every orbit of the Earth, every spacewalk conducted from the International Space Station, all of it combined does not begin to approach 1 light year of distance. Now multiply 1 light year by 2.5 million. The distance to the Andromeda galaxy translates to roughly 14.7 quadrillion miles. 14.7 quadrillion. The number has 16 digits. It is not a distance that yields to analogy or visualization. It is a distance you can only accept as a verified, measured fact while acknowledging that your nervous system has no mechanism for turning it into anything, approaching an image or an intuition. The light arriving at your eyes from Andromeda tonight left that galaxy approximately 2.5 million years ago, Think about what that span of time contains. 2.5 million years ago, the genus Homo did not exist. Our ancestors were small-brained hominins walking upright across the African landscape, without language, without fire, without tools beyond perhaps the occasional found stone. They lived and died within walking distance of where they were born, aware of nothing beyond the immediate horizon. The light reaching your eyes tonight departed before any of that. It left the Andromeda Galaxy before the evolutionary branching that would eventually produce the first hominins capable of making systematic stone tools, before the development of fire, before language, before agriculture, before cities, before mathematics, before the very concept of a galaxy entered human thought. The entire arc of human evolution, every biological and cultural milestone that separates you from a small-brained primate on the African plains, fits inside the travel time of the light you see when you look at Andromeda. That light was already ancient when the first anatomically modern humans looked up at the night sky and wondered what the stars were. It was already ancient when Galileo pointed his telescope at Jupiter. It was already ancient when Edwin Hubble proved, from a photographic plate in a mountain observatory in California, that the smudge in the constellation Andromeda was a separate galaxy entirely. The intergalactic space between the Milky Way and Andromeda is not quite perfectly empty, though it comes very close. Scientists have detected extremely sparse distributions of hot ionized gas, primarily hydrogen and helium, at temperatures reaching hundreds of thousands of degrees. Trace filaments of dark matter thread through the void, remnants of the large-scale cosmic web that connects galaxies across the universe. Occasionally, a star ejected from one galaxy or the other drifts through this space, unbound to any galactic structure, traveling alone through the darkness at hundreds of thousands of miles per hour with no destination and no companions. But the average density of matter in this intergalactic space is roughly 1 atom per cubic meter, 1 atom in a volume, the size of a large cardboard box. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. The difference in density between the air in your lungs and the intergalactic medium spans a factor of roughly 10 to the 25th power. This is not a small difference. It represents a gap so extreme that intergalactic space qualifies as the most perfect vacuum that naturally exists anywhere in the known universe. The most advanced vacuum chambers ever built by human engineers still contain millions of molecules per cubic centimeter. The intergalactic void is emptier than anything we can manufacture. Across 2.5 million light-years of this near-perfect nothingness, no waypoint, no landmarks, no gravitationally significant objects to navigate by, no sources of fuel or raw materials, no electromagnetic signals strong enough to serve as beacons. Something is slowly, gravitationally, inevitably closing the distance. 2 collections of stars and gas and dark matter, each containing hundreds of billions to 1 trillion suns, are drawing toward each other at 250,000 miles per hour. And now we can ask the question this entire journey has been preparing us for. Could any civilization, using any technology, operating under the laws of physics as we understand them, travel from the Milky Way to Andromeda within any time frame that matters to the beings who attempt it? The answer comes not from pessimism, but from arithmetic. Voyager 1, the fastest object humanity has ever sent on an outbound trajectory, travels at approximately 38,000 miles per hour relative to the Sun. At that velocity, reaching the Andromeda Galaxy would require approximately 44 billion years. The current age of the universe, measured from the Big Bang to this moment, is approximately 13.8 billion years. The journey to Andromeda at Voyager speed would take more than 3 times the entire age of the universe. If Voyager 1 had been launched at the moment of the Big Bang, traveling through the infant cosmos before galaxies or stars or planets had even formed, it would still not have arrived at Andromeda by now. It would have roughly 30 billion years of travel remaining. The Parker Solar Probe, which holds the record as the fastest human-made object relative to the Sun, reaching speeds of approximately 430,000 miles per hour during its closest approaches to the Sun, offers somewhat better numbers, 11 times faster than Voyager 1. At Parker speeds, reaching Andromeda would still take approximately 3.9 billion years, roughly the current age of the Earth itself. The entire history of complex animal life on this planet, from the Cambrian explosion to the present moment, fits inside a window of time that represents only a fraction of what the fastest human hardware would need, a velocity that would instantly destroy any material object it struck on Earth. That exceeds the escape velocity of every planet in our solar system. That represents the absolute pinnacle of current propulsive achievement. Purchases almost nothing against a 2.5 million light-year gap. What about future technology grounded in real physics? The Breakthrough Starshot Initiative, announced in 2016, proposed using ground-based laser arrays to accelerate tiny lightweight probes to approximately 20% of light speed, a concept that, even if the engineering challenges are eventually solved, is designed for interstellar distances measured in single-digit light-years, not intergalactic distances measured in millions. But suppose we are generous. Suppose a civilization far more technologically advanced than ours manages to build a craft capable of sustained travel at 10% of light speed, approximately 67 million miles per hour, nearly 2,000 times faster than Voyager 1. No engineering roadmap currently exists for producing this, but grant the assumption. At 10% of light speed, the journey to Andromeda takes 25 million years. 25 million years ago, the ancestors of modern great apes had not yet diverged from the ancestors of modern monkeys. The Himalayas were still being actively pushed upward by tectonic forces. The evolutionary lineage that eventually produced human beings could fit inside this travel time with room. Remaining, pushed the speed to 50% of light. Speed, an almost incomprehensible velocity requiring energy sources, far beyond any currently available to our civilization. The travel time to Andromeda drops to 5 million years. 5 million years ago, the first members of the early hominin lineage were appearing in Africa. Everything that separates those small-brained hominins from you, every tool, every word, every idea, every city, every discovery fits inside the time a half-light-speed spacecraft would need to reach the galaxy next door. And that spacecraft would need to sustain its passengers, or their descendants, or some form of continuously functioning intelligence, across that entire span without failure, without loss of purpose, without the collapse of whatever social and technological infrastructure made the journey possible in the first place. Push further still, 99% of light speed. At this velocity, the effects of special relativity become significant. Einstein's equations predict that time passes more slowly for objects moving at velocities approaching light speed, a phenomenon called time dilation that has been experimentally confirmed with high-precision atomic clocks flown on fast-moving aircraft and satellites. It is not speculation. It is measured physics. For travelers aboard a spacecraft moving at 99% of light speed, the subjective experience of time would be compressed relative to the time passing in the stationary frame outside. At 99% of light speed, with the right acceleration profile, specifically a constant acceleration of 1 g, approximately 9.8 meters per second squared, which would conveniently provide Earth-like artificial gravity, the subjective journey. Time to Andromeda could, in principle, be reduced to roughly 28 years. 28 years of experience time. A crew could, in principle, board in young adulthood and arrive in late middle age. But this scenario conceals problems so severe that they place it outside serious practical consideration. Maintaining 1 g of constant acceleration for the duration of a 2.5 million light-year journey would require an energy expenditure so enormous that no known or theorized fuel source could provide it. We are not talking about difficult engineering. We are talking about energy requirements in the range of stellar-scale power outputs. Second, the travelers who arrived at Andromeda after day 8 subjective years would find themselves in a universe that had aged by 2.5 million years. Everyone they knew, every civilization, every record of their departure, gone for 2.5 million years. The Milky Way they left would be unrecognizable. The very position of their home star within the galaxy would have changed. They would arrive as visitors from a past so distant that nothing from their era would remain. Not exile, something closer to erasure in both directions. Not only would the Milky Way have aged beyond recognition, but the Andromeda they had studied and aimed for would itself have undergone 2.5 million years of stellar evolution during their journey. Stars that burned prominently in their pre-departure observations would have exhausted their fuel and exploded. Millions of new stars would have formed in regions that were cold gas clouds when the mission was planned. The spiral arms would have rotated into different positions. The travelers would arrive carrying charts of a galaxy that no longer existed in that configuration, navigating by landmarks that had moved or vanished entirely. Generation ships, a concept from science fiction that proposes carrying a self-sustaining population that reproduces across the journey's duration, with descendants arriving at the destination, offer a partial workaround to the biological constraints, but run into their own category of impossibility when applied to intergalactic distances. At 10% of light speed, the most optimistically fast generation ship would need to sustain a functioning population for 25 million years. A closed ecosystem capable of recycling all water, air, and nutrients without external resupply for 25 million years. A social structure stable enough to maintain collective purpose across roughly 1 million human generations. A technological infrastructure capable of self-repair and adaptation across timescales longer than most species persist on Earth. Every human being who has ever lived, estimated at roughly 110 billion individuals across the 300 history of our species, were to participate in a relay, each running one leg and passing a baton to the next. That relay would span approximately 300,000 years. The generation ship journey to Andromeda at 10% of light speed would require that relay to be repeated 83 times over, back to back, without interruption or failure. No material we have ever manufactured would survive that duration intact. No social structure in recorded history has persisted for more than a few thousand years without fundamental transformation or collapse. The generation ship concept, applied to intergalactic distances, is not a difficult engineering problem. It is a category error. It applies a solution designed for interstellar distances, where journeys might be measured in decades or centuries, to intergalactic distances, where journeys are measured in millions of years. The two problems are not on the same spectrum. They are separated by a qualitative gulf analogous to the difference between swimming across a river and swimming across an ocean. The distance to Andromeda is not merely a large number. It is a physical boundary, not a wall made of matter or energy, but something more fundamental, a boundary imposed by the geometry of space, the finite speed of light, the energy requirements of acceleration, and the biological and physical limitations of every known form of matter. Within the framework of physics, as we currently understand it, the intergalactic void between the Milky Way and Andromeda represents a permanent separation for any civilization confined to sublight speed travel, not temporarily beyond reach, not awaiting a future technological breakthrough, permanently inaccessible within any time frame that a biological species, a continuous culture, or any coherent line of technological development could realistically sustain. This is not a statement about human ambition or human intelligence. It is a statement about the architecture of the universe itself. The cosmos built its structures on scales that do not accommodate biological travel between galaxies. The same laws of physics that allow stars to form, planets to coalesce, and life to evolve also impose speed limits, energy constraints, and distance scales that confine any civilization born within a galaxy to that galaxy. For all practical purposes, within known physics, the Milky Way is the entire accessible universe for any species that calls it home. And yet the Milky Way is itself not a small prison. It contains between 200 billion and 400 billion stars. Current estimates suggest it harbors somewhere between 100 billion and 300 billion planets, a significant fraction of them orbiting within the habitable zones of their host stars where conditions might permit liquid water on their surfaces. A civilization traveling at 10% of light speed would need 1 million years to cross the galaxy from edge to edge. No species that has ever existed on Earth has maintained a continuous, recognizable technological civilization for even 10,000 years. The Milky Way offers more space, more stars, more planets, more potential destinations, more unanswered questions, and more undiscovered worlds than any single civilization could exhaust in the entire remaining lifespan of the Sun. From where we currently stand, our electromagnetic footprint, the expanding sphere of radio waves, television signals, radar pulses, and other transmissions our species has produced since the early 20th century, extends approximately 120 light-years from Earth in all directions. 120 light-years. The Milky Way is 100,000 light-years across. Our loudest signal into the cosmos covers approximately 0.12% of our own galaxy's diameter. If the galaxy were a dining room table, our entire radiosphere would be a small coin lying on the surface. To any civilization on the far side of the galaxy, watching and listening for signs of other intelligence, humanity does not yet exist. Our signals have not arrived. They will not arrive for tens of thousands of years, and when they do, they will be so faint, diluted by the physics of how electromagnetic radiation spreads through space, that detecting them would require sensitivity far beyond anything we currently possess. There is something quietly extraordinary in all of this, though it arrives from an unexpected direction. We cannot go to Andromeda. No technology governed by known physics can take us there. The distance is too vast, the time too long, the energy too great, the biology too fragile. And yet you can see Andromeda tonight. You can look toward it with your own eyes and gather on your retina the light of 1 trillion stars that has been traveling through the intergalactic void for 2.5 million years. That light left its source before the evolutionary path that would eventually produce you had even begun. It crossed the most perfect vacuum that naturally exists anywhere in the known universe, traversed a distance that reduces every achievement of human propulsion to something entirely negligible, and ended its journey on the surface of your eye, converted into an electrical signal by cells in your retina, transmitted along your optic nerve, processed by a brain weighing approximately 3 pounds, running on roughly 20 watts of metabolic power, housed inside a body that lives for perhaps 80 years on a planet 7,900 miles across. We can see what we cannot reach. We can measure what we cannot cross. We can describe, with extraordinary precision, structures so vast that no journey within known physics could ever traverse them. And we can do all of this from a room, with a telescope, with mathematics, with the same brain that once tracked movement across a grassland. The distances remain what they are. They do not shrink because we understand them. Andromeda will remain at 2.5 million light-years, whether or not anyone on Earth is looking. The Milky Way will continue its long, slow approach toward that light for billions of years, regardless of what happens on any planet, orbiting any star within it. The universe operates on its own schedule, indifferent to observation, indifferent to understanding, indifferent to the presence or absence of any mind capable of perceiving it. And yet those minds are here. A species that spent most of its evolutionary history walking across grasslands at 3 miles per hour has, within the last few centuries, built instruments sensitive enough to detect the gravitational waves produced by 2 black holes, merging 1 billion light-years away. We have measured the transverse velocity of a galaxy 2.5 million light-years from here, to within a few tens of kilometers per second. We have tracked the positions and motions of nearly 2 billion individual stars in our galaxy, cataloging them with a precision that would have been inconceivable to any astronomer in any earlier era. We have imaged the very first black holes ever directly observed by human eyes, resolving structures so small at such enormous distances that the achievement is comparable to reading the date on a coin at the far side of a continent. Before arriving at the questions that remain open, it is worth pausing on the methods by which we came to know what we know about these distances, because the history of astronomical measurement is itself a story about human ingenuity finding footholds in the dark. The challenge of measuring cosmic distances has occupied astronomers for centuries, and the solutions have come not in a single breakthrough, but in a series of overlapping techniques, each one building on the last, extending the range of reliable measurement step by step, like rungs on a ladder reaching ever higher into space. The closest rung is the one called parallax. Hold your thumb up at arm's length and close one eye, then the other. Your thumb appears to shift position against the background. This apparent shift, caused by the different vantage points of your 2 eyes, is parallax, and it grows smaller as the object moves farther away. Earth's orbit around the Sun provides a much larger baseline than the gap between 2 human eyes. By observing a nearby star at 6-month intervals, when Earth is on opposite sides of its orbit, astronomers can detect a tiny shift in the star's apparent position against the far more distant background of other stars. The size of that shift reveals the distance. This technique works well for stars within a few thousand light-years of Earth. Beyond that, the parallax angle becomes too small to measure accurately with ground-based instruments. The Gaia spacecraft, operating above the blurring effects of Earth's atmosphere, has extended the reliable parallax range to stars several tens of thousands of light-years away, covering a meaningful fraction of the Milky Way's disk. In its main mission, Gaia measured the positions and motions of approximately 1.7 billion stars with a precision that, at its best, amounts to measuring the angular diameter of a coin from a distance of several thousand kilometers. It is an extraordinary instrument by any standard, and the data it has produced has transformed our map of the Milky Way's structure, revealing features of the galaxy's spiral arm system and central bar that previous surveys could only partially discern, for distances beyond the reach of parallax. Astronomers developed the method based on Cepheid variable stars that Edwin Hubble used so effectively in the 1920s. The period luminosity relationship, discovered by Henrietta Swan Leavitt, allows the intrinsic brightness of a Cepheid to be determined from its pulsation cycle, and comparison with its apparent brightness yields the distance. This method works to distances of tens of millions of light-years with ground-based telescopes, and the James Webb Space Telescope has extended its useful range further still, resolving individual Cepheid variables in galaxies too distant for its predecessors to detect beyond the reach of individual Cepheid measurements. Astronomers use a type of stellar explosion called a type Ia supernova as a standard candle, a source of light with a known intrinsic brightness. Type Ia supernova are thought to result from a specific physical mechanism. A white dwarf star in a binary system accretes matter from its companion until it reaches a critical mass threshold and undergoes a thermonuclear explosion. Because the mass threshold is determined by the laws of nuclear physics and is the same everywhere in the universe, these explosions are believed to produce very nearly the same peak luminosity regardless of where or when they occur. A type Ia supernova at its brightest outshines its entire host galaxy, making it visible across billions of light-years. By measuring its apparent brightness and comparing that to the known intrinsic luminosity, astronomers can calculate distances to galaxies so remote that individual stars are entirely unresolvable. It was precisely this technique that led to one of the most surprising discoveries in modern cosmology. In the late 1990s, two independent research teams were using type Ia supernova to measure distances to remote galaxies, expecting to find evidence that the expansion of the universe was gradually slowing down, decelerated by the mutual gravitational attraction of all the matter it contains. What they found instead was the opposite. The distant supernovae were fainter than expected, meaning they were farther away than the models predicted. The expansion of the universe was not slowing, it was accelerating. Something was pushing galaxies apart with increasing force over cosmic time. The teams called this unknown component dark energy, and it earned the project's leaders the Nobel Prize in Physics in 2011. What dark energy actually is remains one of the deepest unsolved problems in all of physics. It appears to constitute roughly 68% of the total energy content of the universe, but its nature, whether it is a true property of empty space, a dynamical field that evolves over time, or something else entirely, is not known. The cosmic distance ladder, as astronomers call this sequence of overlapping measurement techniques, is not perfect. Each rung introduces its own uncertainties, and these uncertainties can accumulate across the full range of distances. There is an ongoing tension in modern cosmology between two measurements of the universe's current expansion rate, a number called the Hubble constant, that use different rungs of the distance ladder and produce results that do not quite agree. Measurements based on the cosmic microwave background, the faint afterglow of radiation from the early universe, yield one value for the Hubble constant. Measurements using Cepheid variables and type Ia supernova yield a somewhat different value. The discrepancy, known as the Hubble tension, is now large enough that it cannot be dismissed as simple measurement error, and it has generated considerable scientific attention. Either there is an unidentified systematic error in one or both measurement approaches, or the standard cosmological model is missing something important. Perhaps some new form of physics operating in the early universe, or some additional component of the universe's energy content that has not yet been identified. The resolution of the Hubble tension is one of the most actively pursued problems in contemporary observational cosmology. Cosmic web is another domain where the universe's large-scale structure reveals something both beautiful and disorienting about the scale we are embedded in. Matter in the universe is not distributed uniformly across space. It is arranged in a vast, sponge-like network of filaments, sheets, and nodes a cosmic web that emerged from tiny quantum fluctuations in the density of the early universe, amplified over billions of years by gravity into the enormous structures we can map today. Galaxies are not scattered randomly through space. They tend to concentrate along the filaments and at the nodes where filaments intersect. While enormous regions called cosmic voids, hundreds of millions of light-years across, contain very few galaxies, the local group, containing the Milky Way, Andromeda, and their companion galaxies, sits near the edge of a cosmic filament, a strand of the web along which numerous galaxy clusters and groups are strung like beads. The Virgo cluster, a dense concentration of roughly 1,300 to 2,000 galaxies located approximately 54 million light-years from Earth, sits at a more central location in the local filamentary structure and exerts a measurable gravitational influence on the motions of galaxies throughout the region, including a slight pull on the local group that partially counteracts the general cosmic expansion. The Laniakea supercluster, identified and named in a landmark 2014 study using three-dimensional maps of galaxy velocity, encompasses the Virgo cluster, the local group, and an enormous number of other galaxy clusters and groups spread across approximately 500 million light-years. The name, from the Hawaiian language, means immeasurable heaven. The supercluster was identified not by a traditional boundary in space, but by a gravitational divide, a region where all galaxy motions converge toward a central point, rather than diverging outward toward other structures. Laniakea contains the equivalent of roughly 100 billion solar masses of matter and includes on the order of 100,000 large galaxies. It is one of the largest structures yet identified in the observable universe, and even it is just one component of a larger network of superclusters and voids that stretch across the observable cosmos. The scale of the cosmic web strains even the frameworks we have built to understand the scales. We have already discussed the filaments of the web extend hundreds of millions of light-years. The voids between them span comparable distances. The observable universe, containing roughly 2 trillion galaxies arranged in this intricate, foam-like pattern, has a radius of approximately 46 billion light-years from Earth, a number that exceeds what you might expect from the age of the universe alone, because space itself has been expanding throughout the time-light, has been traveling. Most of the galaxies within the observable universe are receding from us at velocities that exceed the speed of light, not because they are moving through space faster than light, which special relativity forbids, but because the space between us and them is itself expanding. In an expanding universe, the cumulative expansion of all the space between 2 points can produce an effective recession velocity greater than light speed. The light from galaxies beyond a certain distance, the cosmological horizon, will never reach us, because the expansion of space between us and those galaxies is carrying them away faster than light can traverse the growing gap. The observable universe is a finite island of causal contact within a potentially much larger cosmos that lies permanently beyond the horizon of any possible observation. This is a genuinely strange feature of the universe we inhabit. The 2.5 million light-years to Andromeda, the gap we have spent this journey examining, which earlier seemed unbridgeable, is, in the context of the full observable universe, an extremely small distance. Andromeda is essentially in the same local neighborhood, cosmologically speaking. Both galaxies experience approximately the same background expansion, which is why their mutual gravitational attraction dominates over the cosmic expansion in their case, and pulls them together rather than apart. Galaxies sufficiently far apart, separated by distances on the order of several billion light-years or more, are carried apart by cosmic expansion faster than gravity can pull them back together. The local group is internally gravitationally bound and will remain so indefinitely. But the wider universe is expanding, and the more distant galaxy clusters and superclusters are, on average, receding. The stellar populations within the Milky Way itself also tell a story about deep time that helps place our current moment in cosmic context. Stars come in a remarkable range of sizes, luminosities, temperatures, and lifespans. The most massive stars, the blue giants and supergiants, that burn at temperatures far exceeding our sun's surface. Temperature exhausts their fuel in millions of years rather than billions. They live brilliantly and briefly by stellar standards, ending their lives in spectacular supernova that seed surrounding space with the heavy elements produced in their cores. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged inside a star that exploded before our sun formed. The material that makes up your physical being was processed through generations of stellar births and deaths across billions of years, before it became part of the molecular cloud from which our solar system condensed 4.5 billion years ago. The least massive stars, red dwarfs, the most common stellar type in the galaxy, burn so slowly and so efficiently that their lifespans dwarf those of stars like our sun. A red dwarf with half the mass of our sun may burn steadily for 100 billion years, roughly 7 times longer than the current age of the universe. In the very distant future, long after the sun has exhausted its fuel and become a cooling white dwarf, red dwarf stars will still be burning across the galaxy, the last flickering lights in an increasingly dark and cold cosmos. Life, if it can gain a foothold around a red dwarf, would potentially have timescales available to it that make the entire history of life on Earth look like a brief prelude. Between these extremes, the stellar population of the Milky Way spans an enormous range. Giant stars, several times more massive than our sun, end their lives in supernova that leave behind either neutron stars, city-sized objects containing more mass than the sun, spinning hundreds of times per second, with surface magnetic fields trillions of times stronger than Earth's, or black holes, from which neither matter nor light can escape once past the event horizon. The Milky Way contains an estimated 100 million stellar mass black holes, most of them dark and invisible, detectable only if they have a companion star from which they can accrete material and produce X-ray emissions. Neutron stars, for their part, are among the most extreme physical environments known to science. A teaspoon of neutron star material would weigh approximately 4 billion tons on Earth. The pressure at the center of a neutron star exceeds anything achievable in any laboratory, and the physics governing matter under these conditions extends beyond what current theory can fully describe. Neutron stars that pulse in X-ray or radio wavelengths, called pulsars, rotate with such extraordinary regularity that they function as natural clocks of remarkable precision, stable to within 1 part in 10 to the 15th power over long periods. Some pulsars have been used to test the predictions of general relativity in the strong field regime with greater precision than any laboratory experiment. The interstellar medium through which all of this stellar evolution occurs is itself not a passive backdrop but a dynamic, chemically complex environment. Interstellar space contains not just individual atoms but molecules. Hundreds of distinct molecular species have been detected in interstellar clouds, ranging from simple diatomic molecules like molecular hydrogen to complex organic molecules, including amino acids. The discovery of organic chemistry in interstellar space has significant implications for the question of how life's building blocks reach planetary surfaces. Comets and asteroids that formed from the same molecular cloud material as a young solar system can deliver these molecules to a planet's surface during the early period of heavy bombardment that follows planetary formation. The molecular clouds themselves, vast, cold, dark structures thousands of light years across, denser than the general interstellar medium, but still extraordinarily sparse by terrestrial standards, are the nurseries in which new stars form. When a region of a molecular cloud reaches sufficient density, it begins to collapse under its own gravity, spinning faster as it contracts by conservation of angular momentum, heating as the infalling material compresses. Eventually, at the center of the collapse, the temperature and pressure grow high enough to ignite nuclear fusion, and a new star is born. The remaining material forms a disk around the young star, and within this protoplanetary disk, solid particles gradually accumulate into planetesimals, the building blocks of planets. The process takes millions of years, but it is happening continuously across the galaxy. New stars are forming in the Milky Way right now, at a rate of perhaps 1 to 2 solar masses per year. This is a relatively modest rate compared to galaxies undergoing active, merger-triggered starbursts, and it reflects the fact that the Milky Way has consumed much of the easily accessible cold gas that fuels star formation over its long history. The galaxy's star formation rate was considerably higher several billion years ago, during the peak of cosmic star formation activity, when galaxies across the universe were converting their gas into stars much more rapidly than they do today. The scientific questions that remain are not small ones: the precise mass of Andromeda, including the vast, invisible dark matter halo that surrounds and dominates it, remains uncertain within a factor of 2 or more. This matters enormously for predicting the nature of the eventual interaction between the two galaxies. Is Andromeda significantly heavier than the Milky Way, making it the dominant gravitational partner that will determine the merger's outcome? Or are the two galaxies close enough in total mass that the encounter is more of a true collision between rough equals? The answer depends on measurements of dark matter that remain among the most challenging in all of astrophysics. The transverse velocity of Andromeda, the sideways component of its motion that determines whether the first encounter is a direct impact or a glancing flyby, is still being refined. The Gaia spacecraft has produced the best measurements yet, but the uncertainties remain significant enough that the orbital geometry of the approach is not yet settled. Future astrometric missions with even greater sensitivity could narrow these uncertainties considerably, providing a clearer picture of the choreography of what is coming billions of years from now. The dark matter halos of both galaxies, the vast invisible spheres of material that extend far beyond the visible disk of stars and account for most of each galaxy's total mass, are themselves only partially understood. We know they exist because of their gravitational effects. We do not know what dark matter is made of at the particle physics level, despite decades of searching with underground detectors, particle colliders, and space telescopes. The nature of dark matter remains one of the deepest open questions in physics, and resolving it would transform our understanding, not just of galaxies, but of the fundamental composition of the universe. The mechanisms that trigger and sustain star formation during a galaxy merger are also an active area of investigation. We can observe the starbursts that erupt during mergers in distant galaxy pairs. We can model them with computer simulations of increasing sophistication, but the physical processes that compress gas to the densities required for star formation, and the feedback processes by which newly formed stars heat and disperse the surrounding material, are not yet fully understood at the level of detail that would allow precise predictions. Each new observation of a merging galaxy pair adds to the dataset that constrains these models. and beyond the Milky Way and Andromeda. The local group in which they reside sits within a larger structure called the Virgo supercluster, itself now understood to be a component of an even larger structure called the Laniakea supercluster, a gravitational basin encompassing roughly 100,000 galaxies spread across approximately 500 million light years. Beyond Laniakea, the observable universe extends to a radius of approximately 46 billion light-years, containing an estimated 2 trillion galaxies. Most of those galaxies are receding from us, carried apart by the expansion of space itself, at velocities so great that the light they emit will never reach us. The observable universe is itself a finite island within a potentially much larger cosmos that lies beyond the reach of any signal traveling at the speed of light. The Andromeda galaxy is, in this context, extraordinarily close. It is our nearest large galactic neighbor, close enough to see without a telescope, close enough to study in extraordinary detail, close enough that we have measured the motions of individual stars within it, and counted its globular clusters and mapped its spiral arms. In a universe of 2 trillion galaxies, Andromeda is essentially in our backyard, and it is still 2.5 million light-years away. There is a sense in which everything about cosmic scale is designed to humble, not in a diminishing way, but in the way that standing next to something genuinely immense tends to quiet the ordinary noise of self-importance. The universe is not small. It is not built on any scale that human intuition finds comfortable. The distances are real. The isolation is real. The boundaries imposed by the speed of light and the requirements of energy and biology are real. None of this is going to change because we wish it otherwise. But there is also something in the act of measurement itself that resists any purely diminishing interpretation. You are on a planet orbiting a star that is one among perhaps 400 billion in a galaxy that is the smaller of 2 gravitationally bound spirals, separated by 2.5 million light-years of nearly perfect nothingness, itself one small neighborhood within a supercluster of 100,000 galaxies, within an observable universe containing 2 trillion more. And from this particular vantage point, this pale blue speck in the quiet outer suburbs of an average galaxy, the contents of the universe have been measured, not guessed, not imagined, measured, with instruments designed and built and calibrated by the same species that once walked out of Africa with no tools beyond what the landscape provided. The scale is real. The distances are permanent. The limits are genuine. And so, quietly, is the measurement, not as a consolation, but as a fact. A small, 3-pound brain running on the metabolic equivalent of a dim light bulb has looked out across 2.5 million light-years and accurately described what it found. On a clear night, if you go somewhere dark enough, you can do it yourself. Find the constellation Andromeda. Look for the faint smudge near its center. Hold your gaze there and let it settle without urgency, without needing to understand it fully, just allowing the fact of it to rest in your awareness. The light entering your eyes at this moment left 1 trillion stars 2.5 million years ago. It has been crossing the intergalactic void ever since, through the time of the first hominin, through the emergence of language and fire and agriculture, through the entirety of recorded history, through every event and discovery and transformation that has occurred on this planet, traveling at the fastest speed the universe allows, across the emptiest space that naturally exists, and it has arrived here, now, quietly, to be received by you. The universe is vast beyond any comfortable comprehension. It is also, in this particular way, remarkably intimate.